What if I told you that everything you've ever known, your planet, your sun, your entire cosmic neighborhood, might be one of the rarest arrangements in the entire universe? Not just special, not just unusual, but statistically improbable on a cosmic scale. For decades, scientists assumed our solar system was typical. After all, why wouldn't it be? There are hundreds of billions of stars in our galaxy alone, and now we know there are likely trillions of planets scattered across the observable universe. It seemed logical that planetary systems like ours must be everywhere. But the deeper we look into the galaxy, using powerful telescopes, space observatories, and exoplanet hunting missions, the stranger the truth becomes. We are discovering solar systems that look nothing like ours. Giant planets skimming the surfaces of their stars. Worlds locked in chaotic orbits, systems with super-Earths packed tighter than Mercury. Planetary architecture so violent and unstable that Earth-like life might never stand a chance. And suddenly, scientists are asking a question that would have sounded absurd just 30 years ago. Are we living in one of the rarest solar systems in the entire universe? Tonight we're going to take a slow, careful journey through the science, through the data, through the probabilities. And by the end, you may never look at the night sky the same way again. Before we begin our journey, take a moment to gently support the channel. If you enjoy calmly narrated science documentaries that help you relax, think deeply, or even drift off to sleep, consider subscribing. It truly helps more than you know. Like the video if you're ready to explore the universe with me tonight. And I'd love to hear from you. Leave a comment telling me which part of the United States you're watching from. East Coast, Midwest, Texas, California, somewhere quiet under dark skies. Let me know below. Now let's begin. For most of human history, we believed our solar system was the center of everything. The sun rose and set above us, the moon changed shape in predictable rhythms, and the wandering planets traced slow paths through the sky. When Nicolaus Copernicus proposed that Earth orbits the sun, it was a revolutionary shift, but even then, our solar system still felt central. If not physically, then philosophically. It wasn't until the late 20th century that something even more humbling occurred. We began discovering planets orbiting other stars, and what we found was not comforting in its familiarity. It was shocking in its difference. When the first confirmed exoplanet around a sun-like star was discovered in 1995, orbiting 51 Pegasi, astronomers were stunned. The planet 51 Pegasi b was a gas giant roughly half the mass of Jupiter, but it orbited extremely close to its star, completing a full orbit in just 4 days. According to everything we thought we understood about planetary formation, gas giants should form far from their stars, beyond the so-called frost line where ices can condense. Jupiter, in our solar system, orbits at a comfortable distance of about 5 astronomical units from the Sun. But here was a hot Jupiter, hugging its star in a tight, blistering orbit. And it wasn't alone. As more exoplanets were discovered, the pattern became impossible to ignore. Planetary systems across the galaxy were wildly different from ours. Some stars had multiple giant planets packed closer than Mercury. Others hosted super-Earths, rocky planets larger than Earth but smaller than Neptune, orbiting in compact chains. In fact, one of the most common planetary configurations discovered by NASA's Kepler Space Telescope is something our solar system doesn't even have. Tightly packed inner planets, often several times Earth's mass, orbiting much closer to their star than Mercury orbits our Sun. Our system, with its small rocky planets near the Sun and large gas giants far away, suddenly began to look unusual. But unusual doesn't necessarily mean rare. To understand whether our solar system is truly rare, we first have to understand how planetary systems form. It begins with a molecular cloud, a vast region of cold gas and dust floating between the stars. Under gravity, parts of this cloud collapse inward, forming a spinning disk around a newborn star. Within this protoplanetary disk, dust grains collide and stick together, forming larger and larger bodies over millions of years. Eventually, these planetesimals grow into planets. The process is messy. Collisions are violent, orbits shift. Migration can occur. And here's where things get interesting. Modern simulations suggest that giant planets don't always stay where they form. In fact, they often migrate inward, spiraling toward their star due to gravitational interactions with the disk. If Jupiter had migrated significantly inward during our solar system's early history, it could have disrupted the formation of Earth entirely. A migrating gas giant can scatter smaller rocky bodies, ejecting them from the system or sending them crashing into the star. The fact that Jupiter remains in a relatively distant orbit may have been critical to Earth's formation and stability. Some astronomers propose a scenario known as the Grand Tack hypothesis. In this model, Jupiter initially migrated inward toward Mars' current orbit before reversing direction due to interactions with Saturn, eventually settling into its present position. This complex gravitational dance may have shaped the inner solar system, limiting Mars' growth and preserving material for Earth's formation. If that scenario is correct, then our solar system structure required a delicate balance of timing, mass, and orbital resonance between Jupiter and Saturn. Remove one variable, and Earth might never have formed as it did. Beyond formation, there is stability. Our solar system has remained relatively stable for 4.5 billion years. The planets follow nearly circular orbits, reducing extreme temperature swings. The giant planets act as gravitational shields, deflecting many comets and asteroids that might otherwise bombard the inner planets. Although impacts have occurred, including the one that likely wiped out the dinosaurs, the overall environment has been stable enough for complex life to evolve. When astronomers observe other systems, they often see evidence of past chaos-eccentric orbits, tilted planetary planes, and signs of violent scattering events. Many exoplanets follow elongated paths that bring them dramatically closer and farther from their star during each orbit. Such instability could create harsh, fluctuating climates. Earth, by contrast, maintains a nearly circular orbit, varying its distance from the Sun by only a few % each year. That stability contributes to a relatively stable climate, which in turn supports liquid water, the essential ingredient for life as we know it. And then there is our Moon. Compared to other planetary moons in the solar system, Earth's moon is unusually large relative to its host planet. The leading theory suggests it formed after a Mars-sized body collided with the young Earth. The resulting debris eventually coalesced into the Moon. This large satellite stabilizes Earth's axial tilt, preventing chaotic swings that could lead to extreme climate variations over millions of years. Without the Moon, Earth's tilt might fluctuate dramatically, possibly destabilizing long-term climate patterns necessary for advanced life. When astronomers study exoplanets, they currently have limited ability to detect moons, but large stabilizing moons like ours may not be common. The combination of a stable orbit, protective gas giants, a large stabilizing moon, and a relatively quiet star begins to look like a rare checklist. Speaking of stars, our Sun is classified as a G-type main sequence star. It is relatively stable, with moderate solar activity compared to many red dwarfs, which are smaller but far more numerous in the galaxy. Red dwarf stars make up roughly 70% of all stars in the Milky Way. Many of the exoplanets discovered so far orbit red dwarfs. However, these stars are known for intense stellar flares, especially in their youth. Planets within the habitable zone of a red dwarf must orbit very close to remain warm enough for liquid water, which exposes them to strong radiation and tidal locking. A tidally locked planet always shows the same face to its star, creating one permanent day side and one permanent night side. Whether such worlds can sustain stable, life-supporting climates remains an active area of research. Our Sun, by contrast, provides a stable output of energy in a habitable zone located at a comfortable distance where Earth can maintain liquid oceans without tidal locking. So when we step back and examine the data, we begin to see something surprising. Many of the most common planetary system architectures discovered so far look nothing like ours. Systems dominated by close and super-Earths appear common. Systems with hot Jupiters are not rare. Systems with eccentric giant planets exist in abundance. Yet a system with small rocky planets in the inner region, gas giants farther out in near-circular orbits, low orbital eccentricities, long-term dynamical stability, and a G-type star of moderate activity. That combination appears less common in current exoplanet surveys, but we must be cautious. Our detection methods are biased. The transit method used by the Kepler telescope is most sensitive to planets that orbit close to their stars. The radial velocity method also favors large planets in tight orbits. Distant Jupiter-like planets take many years to complete one orbit, making them harder to detect. It's possible that many solar systems similar to ours exist, but we simply haven't observed them long enough to confirm. Astronomy is still young in this area. We've only been detecting exoplanets for about 3 decades, a blink of an eye in scientific time. And yet, even accounting for observational bias, statistical studies suggest that solar systems exactly like ours may not be the dominant configuration in the galaxy. The concept of rarity does not necessarily imply uniqueness. Even if only 1% of stars host systems like ours, that would still amount to billions of similar systems across the Milky Way. But rarity changes perspective. It transforms our solar system from an assumed template into a potentially uncommon outcome of cosmic evolution. As we move deeper into this documentary, we will examine habitability, long-term planetary stability, the role of giant planets in protecting inner worlds, and the probability calculations behind planetary architectures. But for now, in this first chapter, it is enough to recognize that the question itself, are we living in the rarest solar system in the entire universe, is no longer science fiction. It is a legitimate scientific inquiry grounded in real observational data. And the more we look outward into the galaxy, the more our once ordinary home begins to look quietly extraordinary. If our solar system feels increasingly unusual, the next logical question is whether that feeling survives contact with mathematics. Astronomy is not only a science of images and telescopes, it is a science of statistics. When we ask whether we are rare, we are really asking about probability distributions across hundreds of billions of stars. We are asking how often nature repeats certain patterns, how frequently planetary systems settle into stable configurations, and whether Earth-like worlds are common outcomes or delicate accidents. Over the past 2 decades, missions such as Kepler and TESS have transformed our understanding of planetary demographics. Before 1995, we knew of only one planetary system, our own. Today, we have confirmed thousands of exoplanets and identified thousands more candidates. This growing catalog allows astronomers to move beyond anecdotes and begin identifying trends. One of the strongest and most surprising trends is the overwhelming abundance of super-Earths and mini-Neptunes. These are planets with masses between Earth and Neptune, often ranging from about 1.5 to 4 Earth radii. Strikingly, our solar system contains no such planet. We jump from Earth and Venus to Uranus and Neptune with nothing in between. Yet in other systems, super-Earths appear to be among the most common types of planet in the galaxy. Many of them orbit extremely close to their stars, sometimes completing an orbit in just days or weeks. Entire systems have been found where multiple super-Earths are packed within a distance smaller than Mercury's orbit. Statistically speaking, this compact architecture appears more typical than the spacious layout we see around our Sun. That alone raises an important possibility. Perhaps our solar system avoided a common evolutionary pathway. The formation of super-Earth systems likely depends on how quickly material accumulates in the inner disk and how migration processes unfold. In many simulations, inward migration of forming planets causes them to pile up near the star, forming resonant chains of tightly packed worlds. In contrast, our inner solar system remained relatively sparse, allowing 4 smaller rocky planets to form with significant spacing between them. This difference may have profound implications for long-term stability and habitability. Closely packed systems can be stable for billions of years, but they are also more dynamically interactive. Gravitational nudges between neighboring planets can alter orbital eccentricities and inclinations over time. In extreme cases, instabilities can trigger planetary scattering events that reshape entire systems. By comparison, the spacing between Earth and Venus, and between Earth and Mars, provides a gravitational buffer. Our terrestrial planets interact, but not with the intensity observed in some compact exoplanet systems. Then there is the question of gas giants. Observational surveys suggest that only a minority of Sun-like stars host Jupiter-mass planets at distances comparable to Jupiter's orbit. Estimates vary, but roughly 10% of Sun-like stars may possess such distant gas giants. That figure is not vanishingly small, yet it is far from universal. Moreover, the presence of a Jupiter analog does not guarantee a Saturn analog in a stabilizing resonance. Our system-specific arrangement. Jupiter and Saturn in particular orbital ratios that may have prevented destructive inward migration might represent a narrower subset within that 10%. When we combine these probabilities, the picture becomes more nuanced. Perhaps 10% of Sun-like stars have Jupiter-like planets in outer orbits. A fraction of those may also have Saturn-like companions in stabilizing configurations. A fraction of those systems may avoid forming close in super-Earths that dominate the inner region. A fraction may maintain low orbital eccentricities. Multiply enough fractions together, and the percentage shrinks. Yet even a small percentage of a very large number can still yield enormous absolute counts. If only 1% of Sun-like stars have architectures similar to ours, that could still mean millions of comparable systems in our galaxy alone. Rarity is relative. The Milky Way contains perhaps 100 to 400 billion stars. Even rare configurations can exist in abundance on galactic scales. But rarity still matters when we consider life. The concept of the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface, is often presented as a simple ring. Yet true habitability depends on far more than distance from a star. Atmospheric composition, magnetic fields, plate tectonics, carbon cycles, and orbital stability all play essential roles. Earth resides in the Sun's habitable zone, but it also benefits from long-term climate regulation via the carbonate-silicate cycle. Volcanic outgassing releases carbon dioxide, while weathering removes it, creating a feedback loop that stabilizes temperatures over geological timescales. Whether this delicate geochemical balancing act is common remains unknown. Moreover, our Sun itself has followed a relatively calm evolutionary path. Stellar variability can dramatically affect planetary climates. Young stars often emit strong stellar winds and high levels of ultraviolet radiation. Some red dwarfs remain magnetically active for billions of years, producing frequent flares that could strip atmospheres from nearby planets. Our Sun experienced an active youth but settled into a comparatively stable middle age. This stability has allowed Earth's oceans to persist for over 4 billion years. Stability is an underappreciated ingredient in the recipe for complexity. Life does not simply require warmth and water, it requires billions of years of relative calm may be necessary for simple life to evolve into multicellular organisms and eventually into technological civilizations capable of asking questions about rarity. In this sense, the architecture of a solar system becomes intertwined with the timescales of biology. A system prone to frequent gravitational upheaval might reset the evolutionary clock repeatedly. Large impacts can sterilize planets, and extreme orbital variations can trigger global climate catastrophes. While Earth has endured mass extinctions, it has never been completely sterilized since life first emerged. That continuity may not be guaranteed everywhere. Astronomers also consider the concept of the galactic habitable zone, the region within a galaxy where conditions are favorable for life. Too close to the galactic center, an intense radiation and supernova frequency may pose threats. Too far out, and heavy elements necessary for rocky planet formation may be scarce. Our solar system resides in a relatively calm region of the Milky Way, about 26,000 light-years from the galactic center, within a spiral arm but not in a densely packed stellar cluster. Dense stellar environments can gravitationally perturb planetary systems, increasing comet influx or destabilizing orbits. The Sun's relative isolation may therefore be another subtle advantage. When we combine stellar type, planetary architecture, orbital stability, chemical composition, galactic location, and long-term dynamical history, we are left with a multidimensional probability space. Each dimension adds constraints. Each constraint reduces the number of systems that satisfy all conditions simultaneously. Yet it is essential to guard against a cognitive bias known as the anthropic principle. We observe these conditions precisely because they allow observers to exist. If the universe contains a vast number of planetary systems, then even rare configurations will inevitably occur somewhere. We happen to inhabit one such configuration because it permits our existence. This reasoning does not make our solar system common. It simply explains why we should not be surprised to find ourselves in a life-permitting system. The deeper scientific challenge is determining how narrow that life-permitting window truly is. Ongoing missions aim to refine these probabilities. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres, searching for chemical signatures such as water vapor, carbon dioxide, methane, and potentially even biosignatures. Future missions, including proposed direct imaging telescopes, may one day capture pictures of Earth-sized planets orbiting Sun-like stars. With improved data, we will better understand how often rocky planets reside in stable habitable zones around relatively quiet stars with supportive planetary architectures. For now, the statistical picture suggests that while planets themselves are extraordinarily common, the specific combination of factors that characterize our solar system may not be the dominant template. We are not alone in having planets. We are not unique in having rocky worlds. But the precise orchestration of spacing, stability, giant planet placement, stellar type, and long-term calm may represent a narrower slice of cosmic possibility. And yet the story remains unfinished. Our observational window is still biased toward close in planets. We have not yet surveyed enough stars for long enough to confidently measure the true frequency of distant Jupiter analogs or fully map outer system architectures. It is entirely possible that, as detection methods improve and time baselines lengthen, more solar systems resembling ours will emerge from the data. Science is patient. It corrects its own assumptions as evidence accumulates. What makes this moment extraordinary is that, for the first time in human history, we can quantify our cosmic context. We can move beyond philosophical speculation and begin measuring how typical or atypical our home might be. The answer, at least for now, appears delicately balanced between humility and wonder. Our solar system is not impossibly unique, but neither does it appear to be the most common arrangement in the galaxy. It may occupy a middle ground statistically uncommon, yet far from singular. And in that subtle space between common and unique lies one of the most profound realizations of modern astronomy. We are beginning to understand not only where we are in space, but how improbable, or perhaps how quietly fortunate, our arrangement might be. As we continue this journey, we will explore what these probabilities mean for life elsewhere, for the search for intelligent civilizations, and for our understanding of our place in the vast architecture of the universe.